In this video, we're going to look at another example of using the Biot-Savart law to determine magnetic fields of particular current distributions. In this case, we have a current that is in a circle. This is not a perfect circle, but it's supposed to be. So we're going to use our imagination. So I have this current I. It's a loop of current, and hopefully we've seen a few examples so far that will let us know that loops of current can be very useful to us. So we have a loop of current, and what I'm interested in is the magnetic field at the very center of that current. So let me indicate on here where my IDL is, my differential current element. It's going to be here, and I'm going to integrate with the current. So there is DL. Right, IDL is going to be my differential element, but I'm showing you where DL is. It's going to be, this is a circle, and if the current's flowing in a circle, the DL is going to be tangent to the circle. And then, of course, I've got DR, which points from the current element to my observation point, which is there. So this is, I'm sorry, that is R hat. I said DR, I meant R hat. I've got this unit vector pointing from my current element to my point of observation. This, of course, is a distance R. Same thing as we did last time. Let's take care of the geometry here. Notice R is a constant. It's a circle. Circles have constant radii by definition. Furthermore, DL, because it is always tangent to the circle, DL and R are always orthogonal. That's handy. I should say DL and R hat are always orthogonal. That is handy. Let's go ahead and actually take care of that now. We'll see in the Biot-Savart law in just a second when I write it down. I'm going to have to take care of this cross product, DL cross R hat. I will explicitly take care of this soon, but let's just examine here. Notice this is always going to get me, at least at this point, this is always going to get me a vector by the right-hand rule. Fingers in the direction of the first one, curl them into the direction of the second, right? Into DL, curl towards R hat, stick out my thumb. This will always give me a vector out of the page. Let's call that K hat. Why not? Out of page. Oop, out of page, right? We'll call that K hat out of the page, and no matter where I go on this, I'm going to get this vector out of the page. That's handy because we saw in the last video that this is a constant. I should point out on the last video, I called the vector going into the page K hat, and this one I'm calling what's coming out of the page K hat. I mean, you can assign it however you want to, as long as you understand that this is coming out of the page, and the previous one is going into the page. You can call it Harry if you want to, as long as you understand the direction. So, with all that said, with the geometry taking place, let's take care of the DL. We know that DL is going to be a placeholder that's going to take the place of my actual direction. I will replace DL when I write down my integral with what I'm actually integrating over. In this case, I'm integrating over a circle, so DL is probably going to be some DS. I'm using the math language there. For an arc length, we know how to determine an arc length. That's going to be R d theta. And then how am I going to indicate the direction there? Theta hat. Theta hat is a unit vector that always points in the theta direction. How does that work here? Well, DL, if I'm going around theta, this is always going to be in the theta hat direction. Theta hat looks like this at this point. Later it will look like this. Later it will look like this. This is what theta hat does. It always points tangent to the circle. We've already taken care of the tangential nature here by saying that that cross product is always going to get me this vector out of the page. All right, now, with that said, let's be explicit here. The magnetic field at the center is going to be equal to mu naught over 4 pi integral, I'll put in the limits in a second, of I dl cross r hat over r squared. Now this is my general formula. I'm going to match up this from all the work that I did up here. I've already taken care of the DL. DL is going to be written as r d theta theta hat, right? And then our hat will be here. So I can rewrite this as mu naught over 4 pi. Oh, let me take out the current. The current is constant. Mu naught I. Integral, again, I'm going to put it in limits in a second, of dl, which I will write as r d theta theta hat cross r hat divided by r squared. Okay, so I've already figured out that theta hat cross r hat is going to get me this constant vector out of the page. It looked a little bit different. I wrote dl here, but dl is r d theta theta hat. So these are equivalent, right? dl is equal to r d theta theta hat. So I've already figured out that this is going to give me a constant k. So I can pull that out of the integral. R is a constant because this is a circle. R squared is the constant. So I can pull that out of the integral. What is this going to get me? Mu naught I over 4 pi. I'm left with one r in the denominator. I come out with a k hat from the cross product. This leaves me now, of course, with d theta and times the sine of theta, where theta is the angle between these two vectors, right? That's the definition of the cross product. Magnitude of this, which I have as d theta, the r canceled. The magnitude of this vector is r d theta, but the r went away and the d theta is left. Magnitude of this vector, which is just 1, times the sine of the angle between them. But what is the angle between them? It's always 90 degrees, and the sine of 90 degrees is always 1. And so this thing that looks terrible actually just comes out to be d theta. The sine of the angle is 1, magnitudes of these vectors, magnitude of this vector is 1, magnitude of this hat vector is 1. The magnitude here is just d theta because the r canceled here. This just leaves me with d theta. Now I'm ready to put in my limits. I'm going to integrate over the whole circle. We might as well just go from 0 to 2 pi. This is a pretty easy integral. The integral of d theta is just theta. So what you get out of this is mu naught I over 4 pi r k hat theta evaluated from 0 to 2 pi. 0 at the lower limit, 2 pi at the upper. This 2 pi is going to cancel with 2 pi here, leaving you with a 1 over 2. And what you get out of this is that the magnetic field at the center is mu naught I over 2 r, where r is the radius of the circle, and then k hat. In this case, out of the page. You might be able to convince yourself that if the current was running the other way, it would be into the page. All right, so if you go to your formula sheet and look up the magnetic field at the center of a coil of wire, you get mu naught I over 2r, where r is the radius of the circle. So this is where that formula comes from. On the last problem, we saw where the formula for a long straight wire comes from. This one we saw where the formula for the magnetic field at the center of a coil of wire comes from. I should point out, this is only valid at the center. If I get away from the center, r is not a constant. A lot of the work here was done for me because r was a constant. If I am away from the center, r is no longer a constant, and my equation is not this pretty. But as long as I stay at the center, this works.